Hi everyone, my name is Ping-Hsuan, a PhD student in computer science from U of I. Today I'm presenting a work collaborated with Lawrence Livermore on accelerating kinetic simulations of electrostatic plasma with reduced order modeling. So why reduced order modeling? Kinetic description of plasma is required in many engineering applications, for example, designing and simulating fusion energy device. Thanks to high-performance computing and advanced algorithm, we are now able to run high-fidelity simulation, for example, a 3D turbulent orthogonal fusion device with 200 million degrees of freedoms. However, when it comes to multi-query applications, the computational cost is prohibitive because it requires hundreds of simulations. Reduced order modeling therefore provides a potential rapid turnaround tool for this kind of engineering query. Our mathematical model is 1D 1V Vlasov-Poisson equations with parameterized initial distribution by the perturbation amplitude alpha, temperature T, and initial stream velocity V0. The forward models are finite by high-dimensional ODEs with unknowns from 10,000 to millions, which is usually derived from classical numerical method. In this talk, we'll be focusing on a classic two-string instability model problem used to study instability generated by two counter-streaming beams. For our reduced order model, we consider a data-driven approach where we use high-fidelity solution to construct the reduced basis function. The reduced basis function are then used to approximate the forward model solution F. By substituting the approximation into the high-dimensional ODEs, and with Galerkin projection, we derive a low-dimensional system similar to a forward model but with only 10 to 100 unknowns. So far, we have gone from mathematical model which live in the Hilbert space with infinite unknowns to forward model of finite by high-dimensional ODEs, and to reduced order model, which is a low-dimensional ODE with 10 to 100 unknowns. However, there are two challenges with the standard ROM. First is due to the nonlinear term G, where the evaluation requires reconstructing the field which depends on the forward model size, therefore no speedup in the ROM. Second is that the problem is multiscale. Here we are showing the behavior of the maximum absolute value of E with several parameters. For each parameter value, there are three solution stages: single mode, nonlinear, and statistically steady state. In addition, the growth rate depends on the parameters. Therefore, we propose a time windowing ROM with tensorial approach. The idea is to partition solution manifold into multiple time windows and build a local ROM for each window. The tensorial approach is to remove the forward model dependency when evaluating the nonlinear G. With the tensorial approach, the nonlinear term can be approximated by the matrix plus a tensor which only scales with the reduced system unknown. The tensorial time windowing ROM is efficient and is also expected to have the capability to capture the multiscale behavior. We built the tensorial time windowing ROM with 4 forward model datasets and tested on the 2D parameter space. The solution time interval is from 0 to 10, including the 3 solution stages. In the following table, we show the relative error in the solution versus the parameters. The 4 red boxes are training data that we use to build the ROM. The tensorial time windowing ROM is able to achieve 4% error in training data, while a maximum 30% error in testing data, and obtain about 280 times speedup. We further look into the behavior of the predict maximum absolute value of E by the tensorial time windowing ROM. The solid line is the forward model, and the solid dashed line is the reduced order model. We find they can not only capture the growth rate but also capture the peak value. Here we are showing the predicted solution for interpolation and extrapolation cases at t equals to 8 and 10. We could see that for the first case, it predicts the solution accurately, and for the second and third cases, despite some discrepancy in the solution, it can capture the overall shape and also the occurrence of the instability, which is at t equals to 8. If you are interested in our work, you can find more details in our paper.